In the earlier lecture, I talked about space-time symmetries. Now, today, I will talk about that what is space and time in basically Newtonian mechanics. Here, let me do one thing. Yeah, let me arrange the camera. Yeah. So, let me first of all talk about that what is space. So, in Newtonian mechanics, that space is often conceptualized as three-dimensional Euclidean space, and that provides a fixed reference frame for describing the motion of objects. And what are the properties of space? Space is three-dimensional and Euclidean, and it has length, width, and the height, and it follows the rules of Euclidean geometry. So that means it's basically a three-dimensional Euclidean space. So first of all, let me briefly talk about that. What is Euclidean space? So Euclidean space is a fundamental concept in geometry, and that represents the family of three-dimensional space we experience. Uh, we experience, and it is characterized by the following properties. It's a its property is three-dimensionality, and it is length, width, and the height. And this Euclidean space is a Euclidean geometry, means it follows the rules of the Euclidean geometry, meaning parallel lines never intersect, and shortest distance between 2 points is a straight line. And this leads to another very interesting property, that is the flatness of space. And another is absolute, means it exists independently of any matter or the observer. And it is homogeneous, so it has same properties at every point, and it is isotropic, it looks same in all directions. Let me briefly talk about these two properties now separately, because they are very important properties. So first is the space is uniform and has the same properties at every point. In simpler terms, there is no preferred location in space, means every location is equally preferable, or you can say that the every law of physics will remain same in everywhere. Consequence of this leads to the law of conservation of linear momentum. Then another is a very important property, that is isotropic in space. So it is basically related to every location, but this law is related to in all directions, means space is same in all directions. In simpler terms, we can say that there is no preferred direction in space, or no direction can be differentiated from the other. And consequence of this is that this law leads to the law of conservation of angular momentum. This is a very important consequence of this. Now, next is a time. So in Newtonian mechanics, time is considered to be an absolute and universal quantity, flow uniformly independently of any physical process or the observer. And let us have a look at the few properties of time in Newtonian mechanics. It is absolute, it is universal, one-dimensional, and independent of space. Means time exists independently of any physical process or observer. It flows uniformly, consistently throughout the universe. And time is same for all observers, regardless of their relative position or location or the motion. And it is one dimensional, means time is considered as a single dimension and progressing in one direction from the past to the future. Independent of space means time is not influenced by the spatial dimension, it flows uniformly regardless of the spatial locations. Now let us have a look at two very important properties. One is the homogeneity of time, and another is the isotropy of time. This homogeneity of time is a very important property, that homogeneity of time in the Newtonian mechanics means that laws of physics remain same at all times. In other words, there is no preferred moment in time. And a very important consequence of this is the conservation of energy, and homogeneity of time is directly linked with the conservation of energy. And if the laws of physics were different at different times, energy would not conserve. Means that that all the laws will remain same at different times. And if it doesn't happen, that means energy of the system will not conserve. Then isotropy of time. Isotropy of time implies that laws of physics remain same regardless of the direction of time. In simpler terms, if a physical process can occur in one direction of time, it could theoretically occur in the reverse direction as well. Implication of the isotropy of time is time reversibility. Say, for example, many classical mechanical processes are time reversible. For example, if you record a video of ball being thrown up and falling back down, you can play that video backward. Means if I play that video backward, the reverse motion would still again obey the same law. Conservation laws. Isotropy of time is closely related to the conservation law of energy, momentum, and the angular momentum. And these laws hold true regardless of the direction of the time. Means in the earlier time, in today's time, the present time, or in the future time, that those laws of conservation will remain equally valid. But there is another aspect of looking at this space and time. In classical mechanics, these space and time were considered separate. However, Albert Einstein's theory of relativity gave a new concept. Means he clubbed both space and time. According to the relativity as suggested by Einstein, that space and time are not separate. Means it leads to the uniform entity. And Einstein merged these three dimensions of space and the one dimension of time, and this leads to the four-dimensional continuum called space and time. Means Einstein clubbed space and time. Means, but we are not going to talk about in this chapter this space and time continuum. We will separately consider space and we will separately consider time. And there is an interconnection between space and time and are not independent but are intertwined and influence each other. Curvature is a very important thing. There is a curvature in space-time. Means massive objects curve the fabric of space-time, affecting the motion of other objects. This is a very small book which I am going to share with you regarding this. Means regarding this what we call curvature. So let us have a look at that. It's a very interesting book by General Relativity for Babies. Is Chris Ferris has written this book. Say, for example, I'm just showing these certain screenshots with you. This is a ball, and this ball has a mass. It's more mass, less mass, and this is a flat space. This is a Euclidean space. But according to what will, if you put some mass into this flat space, then this swaps the space. This like this, as it is shown here. Less mass means less swap. More means more. This is a small particle and it must follow this path, but it cannot, because of this strapping of space. It goes closer, round and round, round and round, shortest path through the curved space. And this ball is spinning. Mass drags space, space drags mass, and flat space from different angles, and the mass swaps space from this angle. So like this. And this concept, general theory of relativity, leads to new concept of say leading towards the black hole and the singularity. This is a very interesting thing. So here in the earlier slide, as I show you, this is basically curvature. Means massive objects curve the fabric of space and time and affecting the motion of other objects. So I think that's all for today, and in the next lecture I will talk about various properties, that how this homogeneity of space, isotropy of space, and the homogeneity of time leads to the different conservation laws. So in the next lecture I will derive various laws. Thanks for watching this video.